Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 9.7, Simple Harmonic Motions. Simple harmonic motion, or SHM, is used everywhere in science. It's a really good approximation to small oscillations with a tiny amplitude, and it's very common in physics. It is essential that you know what an SHM equation looks like, roughly speaking, but you're not really supposed to know how, why SHM happens in physical phenomena, as long as you can just find the general equation of the simple harmonic motion, then push it forward to solve for your general solution. With that said, let's have a look at an example. Okay, so I'm sure you know how to solve for this equation already. It's simply an imaginary solution to the auxiliary equation, which means that you get a sine and cosine solution. That's all fine, but the important thing about simple harmonic motions is that there are some values that you need to kind of understand. There's a physical relationship between the equation and the solution, and so you just have to kind of get a hold on what they really mean in the physics sense. The ones who've done physics A level, or who's doing physics A level, would find this relatively straightforward. The ones who have never really concentrated in physics class might find this a bit of a struggle. I'll try my best to help. So first of all, this equation can be written in the form of acceleration equals to a negative arbitrary value of the displacement from, equilibrium. So in physics, this kind of scenario will be thought of as, let's see, I have a string hanging with a mass, and if I displace the mass upwards, then our string would be extended, vice versa. But in this scenario, on either case, if I displace my object upward, then the tension of the string will pull the acceleration downwards. Acceleration denoted by double arrows, by the way. For the scenario where you have the displacement downwards, you have the acceleration upwards. Which means that according to physics and the notation for physics, direction is the positive/negative, and doesn't matter which direction you're talking about. For all, acceleration equals to a the negative direction of a displacement. And for this scenario, if you do the actual calculation of the F equals ma, you will get something along the line of the acceleration equals to a value of displacement, given that there are no damping forces, which I'm gonna talk about next time. So this will result in a differential equation such that we have a simple harmonic motion, and the frequency and time period of the oscillation are determined by some factors along the lines of the tension and other cases which makes up this value. This value is very important. If I'm not mistaken, it involves the spring constant with the mass in the oscillating mass on a string. But there are a lot more cases that this would work, such as let's see, pendulum swings. There are chemical oscillations, the vibrating of sound waves, etc. Like all of those in small values are basically simple harmonics. So let's have a look. This value here, the 4, can be written as omega squared, and so the general formula for simple harmonics, which I'm gonna call simple harmonic motion, simple harmonics for short, it would be acceleration equals to negative omega squared x, where x is the displacement, and the omega is not, I didn't write the omega square for no reason. The fact is that in physics, omega is equal to 2 pi over the time period, or it's also 2 pi times the frequency, where 2 pi is obviously radians and frequency is how many times does it complete an oscillation per second. And for you to solve this solution, you'll get a trigonometry along the line of cosine of omega t. That's of course the A plus the B sine omega t. If we take a real look into this whole thing for simple harmonics, we don't need to care about the particular integral. There isn't one, because it's simple harmonics. It's not forced harmonics, which will be something else that you do not actually need to know. But if you do physics, you would need to know how to do forced oscillations. I'm gonna skip that. So this is your general solution for simple harmonics, as we all know, for x equals. They are trigonometric oscillations, and the omega corresponds to this within the trigonometric function, which means that the smaller your omega, the longer it takes for your wave to propagate compared to a high omega. You'll get something similar to that. Combining two tricks would give you a different amplitude, but that would also be the same as your compound angle during normal A level, at least I think. Yeah, it's not GCSE content, so if you want to find the maximum amplitude for a simple harmonic motion with a strange solution like this, then you can give your equation a remake into a compound angle, and so you'll get something along the lines of r cos or sine of omega t take alpha or something. Yeah, basically you get something along the lines of these kind of expression, and this will directly correlate to your maximum amplitude, which is helpful to know in some of these equations. But I think for simple harmonics, it often only have one or the other for sine and cosine, because normally you start at a zero. You have initial conditions, as I've talked to you about before, and for a physical scenario there are always initial situations. They will tell you that it started t equals 0 when the amplitude is an arbitrary value of u1. No, u should be the initial speed, shouldn't it? So it would normally have a displacement initial of x, where you have it stationary, which means that initial velocity is 0. Then you calculate with the forces to get the F equals ma, solve for the motion, and eliminate a or b, basically. So with that said, that's all. I think that's all for simple harmonics. So for simple harmonic motions, it's very important that you remember that omega is equal to 2 pi on t, or 2 pi f, where f is the frequency, t is the time period, 2 pi is just number, omega is the angular frequency, as we said. It's helpful to look at a lot of past questions, especially past paper ones, to understand how to use F equals ma to derive these equations, because for the simple harmonic motions they will always give you a case study scenario rather than just a bunch of numbers that you need to calculate. Unlike second order, sometimes in the paper they will give you a question which is literally just algebra and tell you to find the GS and whatnot. So it's not really that difficult in comparison to these physics related questions where you need to actually know what they mean. So yeah, that's tips, and let's get on with some questions. So I derived the questions from a past paper question, and I have this scenario, and you need to find the differential equations that's shown on part 1. I've stated the initial condition for the particle where it's velocity 0 with displacement 5. So find the solution from that information and state the amplitude and time period. Give it as a... Actually, I'm gonna turn this into just a... find the solution in terms of the algebra, then also state the amplitude and time period in terms of A. I will show you the answer in 5, 4, 3, 2, 1. And here we have the solutions. It's really quite straightforward. It's simple harmonics. It's supposed to be simple, and the questions for simple harmonics should almost always look like this form. So it should be okay for anyone to do without a problem. It will get a bit harder for damped oscillations, which I'm gonna talk about next time, but for now, thank you very much for watching. If you have any questions, do let me know in the comment section below as usual, and I will see you on my next one.